Hey everybody, in this video we're going to be exploring allocate from the Rookies section on pwnable.kr. Let me give you a lesson, how to prevent buffer overflow. And we have this SSH link here. So first thing we can do is just go to the link and see what we have. We have a pretty standard directory here with the flag and then a binary as well as the C source file. So let's go ahead and just look at what the source file looks like. We see here there's quite a bit, so let's just start with main. We have printf. Buffer overflow is very easy to prevent. Here's how. 1. Allocate the buffer size only as you need, and 2. Know your buffer size and limit the input length. Simple, right? Let me show you. What is the maximum length of your buffer in bytes? And then here we have a scanf %d into size, which is declared as an integer globally. Then we have give me your random canary number to prove there's no buffer overflow, and we get to enter that as a decimal number as well. So a thing I'd like to point out at this point is that typically when you have a canary to kind of check for buffer overflow, what you want to do is have the process generate its own canary value that's unknown to the user, because only in this way you can guarantee that the user hasn't overridden the canary with something that they have knowledge of. If you're implementing canary where the user gets to just input their own value, then there's really no point in implementing this, because once the buffers overflow, the canary can be just written to what it was before to bypass any checks for the canary. So I just wanted to point that out really quickly. And then we have here, okay, let's allocate a buffer of length size, and we have a call to allocate of size +4. So the +4 here is presumably for the canary to be tacked on at the very end. And indeed, now let's put the canary at the end of the buffer to get your data, and we have the mcopy 4 bytes from the canary global to the buffer plus size. And then we have, don't worry, fget securely limits your input after size bytes. And indeed, we have a call to fgets here. And theoretically, if everything works as it's supposed to, the fgets indeed will limit the input to size. So again, it's kind of surprising, because it doesn't seem like if we use this program correctly, there's any way we can really get anything interesting to happen here, because we have an fgets instead of, for example, a dangerous function like gets. But in any case, we have printf. Now let's check the canary to see if there was overflow, and it seems that we call check canary with the value at buffer plus size. So check canary seems to be a pretty simple function. We just have a result that's equal to the XOR between canary and G canary, and obviously if those are identical to each other, in other words, if the canary was unchanged before and after the call to fgets, then we have printf I told you so. It's really easy to prevent BOF, therefore as you can see it's easy to make secure software. And otherwise it's going to display how did you mess this buffer? Yeah, so, but really what we can see is nothing really happens in either case. It's just a print. And the result is returned, but it's not really used by main here. So not really sure what's the big idea here, and then we just return at the very end. So if looking further up, we see there's a function call me that runs system bin_sh, which is probably what we need to be targeting. It's not called anywhere within main or check canary, but it's something that we probably need to get running. And then we have a trivial function here that appears to just append a new line perhaps after the end, or yeah. Okay, so that's the entire C source. So to get a better idea of what's going on in this program, and especially how we can exploit this program we can secure copy the binary allocate into a local directory and open it up with IDAPRO. So here's the main function disassembled in IDAPRO. We can see immediately that it's from the graph overview here that it's just a linear function here, nothing special. And from the comment at the very beginning, the attributes, we see it's BP based, fuzzy SP. And although I don't really know what fuzzy SP means, like what that's specifically referring to, but one thing we can automatically see when we look through this disassembly is that everything in terms of the stack is done relative to ESP. And you can see that for pushing arguments and for removing arguments from the stack with the add ESP hex 10, we see everything is done relative to the stack pointer. Instead of typically what we see is referencing in terms of the base pointer. So this is interesting. And in fact, if we try to cross-reference the base pointer register, we see it's only used once, twice, and 3 times throughout this entire function, just in the beginning and the end here. So that's something to be watching out for. So into the entry of this function, we have a push, or first we have an alignment operation with ESP to a 16-byte field here, which is typically nice to have. And then we have a push and another push, a push EACX minus 4 and a push EBP, and then a move EBP from ESP. So this is kind of standard. These two are kind of standard. So from this, we can kind of see now, kind of develop a relationship between ESP and EBP. So we have 2 pushes after the alignment, which means that EBP now is, or EBP and ESP now are going to be 8 offset from a 16-byte aligned field. After this move, we have a push ECX and a subtraction of 4 from ESP. So this now, after this instruction, we have ESP now back aligned, but it's 8 below EBP. So base pointer is now pointing 8 above the stack pointer. Past this point, we have a subtraction of ESP of 0C, which is decimal 12, and then a push and a call and an add 10. So, and then this kind of repeats throughout the rest of the beginning here, which kind of indicates to us that whatever ESP is by the end of this instruction is kind of the set value of ESP, the base of the stack, but really it's the top of the stack because stack grows up. That is until we get to this convolution here, this long segment of code, and if we kind of reference what this is going at in the C program, we see it's after the sleep here, which is the call to allocate. And in fact, that is the name of this challenge, so we should probably pay close attention. First thing we can comment about what we see in the disassembly versus in the C program is that allocate is not a function that we call, for example, like puts or sleep or something like that. Rather, it is just a bunch of assembly code that is just stuck in the program like this. And the reason for this is just the way that allocate works. So if we go into the Linux terminal and type man allocate, we see that the description is allocate memory that is automatically freed. So this already sounds kind of interesting because, for example, typically when we try to allocate memory, it will be on the heap, in which case we first have to allocate it and then free it later on. But let's reading further, we can see the allocate function allocates a certain number of bytes of space in the stack frame of the caller. This temporary space is automatically freed when the function that called allocate returns to its caller, obviously, because the kind of stack implementation will take care of that automatically. So this will give us an insight why this happens and not, for example, a a push of the size and then a call to a function called allocate, because this has to be created in the stack frame of the program. If we call another subroutine, then the allocation will not have any effect on the stack pointer. So now that that's established, let's look at exactly what happens. So let's go through it really quickly. We have a move of size into the EAX, and then we add 4, and then we add 15 and move the result into EDX. So now EDX, as you can see, contains size plus 19, because 4 plus 15 gives the 19. After that, we have move EAX 16 and subtract 1, so that's actually EAX is 15 now. And we add EAX to EDX and store the result in EAX, which means that EAX now contains size plus the 19 plus the 15 here, which is actually size plus 34. So that's size plus 34. And then we move 16 into ECX, we clear EDX, and this sets up for a division by ECX. So we divide the result by 16, and immediately after that, we multiply the integer quotient by 16. So as you can see, what happens here is essentially we just get alignment with a 16-byte area in memory. The next instruction is the crucial one, and typically it's the one that people cite as being the heart of allocate, and it's the subtraction of EAX from ESP. If we run this normally and make sure that EAX, or at least EAX plus 34, as we saw up here, and then manipulate it aligned with these instructions here, is a positive value, then ESP will point further up in terms of memory. Up means lower addresses, which is normal because we've just allocated a bunch of space between our original frame, and the stack pointer. But suppose now that EAX were not positive, but were rather negative. And this is completely possible. You can see that because if size contains something that's sufficiently negative, then after we add the 34 and then do this manipulation here, we will get EAX containing a negative, and the subtraction will now move ESP down in the memory, which means higher up in terms of addresses. And this is detrimental to program behavior because now the stack frame, which essentially depends on ESP, is now moved to a location that is not meant to be. So you can see here that everything else, the function calls after this, reference the ESP that was generated here. We have subtraction of ESP hex C, and then a push, call, and remove. So every one of these subsequent function calls references that ESP. So if we can somehow get ESP to point lower in memory, these function calls will violate the stack formalism and will allow us to perhaps write over, for example, the return pointer. So let's figure out how we're going to overwrite this return pointer here. So down here we have in the kind of the leave segment here, we have EBP minus 4 loaded into ECX. And then we have leave, but then we have ECX minus 4 loaded into ESP, and then return. So return will just jump to whatever ESP points to. And ESP is controlled by ECX minus 4. ECX is controlled by EBP minus 4. So what we want to do is somehow get these functions previously to kind of overwrite EBP minus 4 in the mainframe. So to do this, let's check out the last function that was called. In this case, it's check canary. So in check canary, we see there's a lot of local variable assignments, and interestingly, check canary is a BP-based frame, and you can see that easily because everything is referenced in terms of EBP. All the function calls except for these, but in terms of the local variables, we still have reference via EBP. Now, the function calls are still seem to be referencing ESP, but anyways, Specifically here, the assignment of the canary directly to a local variable, ebp minus x14, is noteworthy. So we can see here that if the function that called this had the stack pointer messed up, then ebp minus x14 may actually allow us to point to ebp minus x4 in the main stack frame. So to see how this works, we have to do kind of a dirty work of backtracking. So let's open up Paint, the most excellent drawing program, and kind of elucidate the relationships among these pointers here. So again, we have EBP, and I'm gonna call this one EBP in the check canary. So I'm gonna call it just C, minus hex 14. This will give us the canary. And we control this canary, remember, because we directly get to input this, which is why I said it was useless to begin with. So how is this EBP related to EBP in the original stack frame? Well, to figure that out, we can probably begin by relating EBP in C to ESP at the very beginning of C. So if we look at ESP at the very beginning up here, we can track what happens to it. So first, push EBP will decrement it by 4. Then move EBP ESP will set it equal to EBP, and since EBP doesn't change after this point, only the values that it points to, then we can say that at this point, ESP minus hex 14 also points to G canary. But that's at this instruction. If we move back one instruction, that means we have to decrement it by 4. So actually, EBP minus hex 18 will give us the same thing. So again, ESP at C, I mean the stack pointer at this location, the first instruction, before executing the first instruction of check canary. So this is powerful because now we can go back to here and actually find the relationship between ESP here and the ESP at that point. So let's just call this ESP main 1. We know that during a call, the stack pointer is decremented by 4. So ESP M1 decremented by 4 will give us whatever ESP at C is. And then after this point, we can now generalize to the normal base top of stack kind of base of frame pointer, because these instructions, as we've seen multiple times before, kind of make sure that the stack is aligned. But before the subtraction here, we really have our stack pointer. So our ESP, I'll call this now M2, we can see it's first subtract 12 and then another 4. So that's actually hex 10 will give us ESP at M1. Now let's go to the very beginning here and notice that I mentioned that the stack pointer was constant up here but changed as a result of allocate. So we can now relate the stack pointer here with the stack pointer up there. And remember I said that ESP at this M2 will be equal to ESP at, let's call M3. M3 will be the stack pointer after it's aligned at the very beginning. So in which case it's here, ESP before here. It's ESP at M3 minus, so this is a minus, minus the size plus 34 and this is decimal, aligned to the 16. So we won't worry about that. We'll assume that we're going to just input sizes that will make this a multiple of 16 such that this is just the case. Wow, so now we have quite a few relationships here. But we're still not done because we're just trying to target EBP in the main And we can actually easily relate that with ESP at M3, because we know that ESP at M3 is just going to be 8 under EBP, because it was ESP here was decremented by this push and this subtraction. So we have a bunch of relationships here, but we can kind of make sense of them by just using some intuition and some really simple computation. So again, our goal is to try to get G canary here equal to EBP minus hex 4. So let's start down here and notice that, let me make this a little bit bigger. So first notice that EBP M minus 4 is ESP at M3 plus 4, right? So that just minus 4 from the both sides here. And moving forward, so then moving here, we see that ESP at M2 is simply equal to, let's see here, the size plus 34, ESP M3 minus size plus 34. Okay, maybe that's not the best way to do this. Yeah. So what we want to do essentially is make sure that size will allow for ESP minus hex 4 to be size will allow for EBP minus hex 4 to equal EBPM minus hex 4 to equal EBPC minus hex 14. So it's kind of convoluted in what we're trying to do here. But for example, let's start from up here maybe. And notice that since ESP, okay, first from here we can deduce that ESP at M1 is equal to EBPC nope, it's not correct. ESP M1 minus hex 4 equals ESPC, but ESPC minus hex 18 equals G canary. So ESP M1 minus hex 1C gives us the target value. And continuing this, we see that ESP M2 minus hex 10 equals ESP M1. So that means that ESP M2 minus hex 2C equals the target value. And so now we're getting pretty close to solving this. We finally know that ESP at M2, if we want this to be equal to that, then we got to make sure that this is equal to this. And for this to be equal to this, we can solve that out finally to be that ESP M2, right, equals ESP at M3 plus 4 plus 2C, so that's plus hex 30. And so we see that the forms of these two equations are very similar. So this one here that I wrote earlier, as well as this one here that we solve based on what we're trying to set equal to each other. And this will give us the size. So ESP M3 minus size plus 34 versus plus 30. So clearly here size is negative. And to make it, so 30 is actually 48 in hex or in decimal. So if we want it to be, so this tells us that negative size, actually size plus 34, we can just take negatives, equals negative 48, such that size should be negative 82. Wow. So by this deduction, if we have size equal to negative 82, then our canary that we input will be set to EBP minus hex 4 in main. So let's go ahead and just check this out, and then the exploit will come naturally. So we're gonna use GDB here. Oops. Quickly. Okay. GDB allocate, and let's go ahead and let's see. We're gonna break after check canary here to check what EBP minus hex4 contains. So let's break at 804.8.829. Okay, and oops, that's not the right address. Let's just try again. Okay. Oh my gosh. Okay, so let's run. And we see the program running. What's the maximum length of your buffer? Oops, negative 82. And a random carry number, let's just say something like 5432. Okay, and after calling the check canary, we see, how did you mess this buffer? So now let's look at the registers, and let's look at, so we see it's about FFC 27 or so. So let's examine one word from EBP minus hex4. And we see that it's hex 1538. If we check what that equals in decimal, we see that it's 5432. So we see that we've successfully overwritten EBP minus hex4 with that. So continuing on in the program, we see that next we have to execute move 0 into EAX, and then we're moving EBP minus 4 into ECX. So we should see in two instructions that ECX will contain oh, we didn't execute that instruction yet. Okay. Yeah, now ECX contains 5432. And then we execute leave. And then we execute we move ESP. Let's see. Okay, we have to return. But before that, we have a load effective address of ESP ECX minus 4. So ECX minus 4. Okay, yeah, I see that here. It's yeah, that's correct. So it's hex 1534. But of course, that doesn't point to anything. Oops. Yeah, cannot access memory at there. So when we return, we'll get a seg fault probably. Yeah, seg fault. But we can make this point to something that contains a valid return address. And even though we don't control a buffer, we of course have the environment variables that we can use as kind of a large space to put in inputs. So based on what I see here from the stack, it's about in the FFC region. So our environment variable should be, let's say around FFC 8000 or something around there. We can be pretty confident that that's the case. So we can return to that location. So let's go ahead now that we have an idea of what we're going to do, just craft an exploit for this. So go to temp to make sure that you can actually write stuff, and create a Python from pwn import all. And first thing we gotta do is get the actual pointers. Oops, to the call me function here. So let's see. So here's call me. We gotta get a bunch of pointers to here. So this is at 804.858b. So like this. Okay. So that's packed 32, and we make a spray equal to I didn't assign anything to this. So that's call me. And let's make this a huge number, 30,000 or something. So this will be duplicated 30,000 times. And then we can make an environment. So environment. So what we can do is just something like a mapping from just a text like 0 to, I don't know, however big we need to make it. Let's just try 10 at first. 30,000 is quite a lot. So let's try that. So to SP for I in range 10. So this will give us essentially 300,000 pointers in the environment section, which should be more than enough, but we'll see. Okay, so after we create our environment, we can start a process. And our process will be located home, Alloca, and with our environment set to E. Okay, right here, and that looks good. So first, we have to send line our size, which is -82, and then we have to send line our canary, which will actually be a pointer, which we can use a calculator to determine. So we're in 32 bits, so change this to the double word, and we wanted something at C80000. So we can see from converting to decimal that this is about -3 million here. And this must be entered as a decimal because if you saw in the C program, it was reading in a %D format. And if we're successful, we should have called call me, in which case we can just run it. So let's try it out. Okay, we get this. What's the 2? Okay, so we stopped with exit code -11. And we got it in the file, so let's try that again. Perhaps we jumped to the wrong spot. Got another end of file. Okay, that's the third time. Maybe run this a couple more times and then have to look into changing some stuff. Okay, so it's not seeming to be working right now. So let's try another. Oh my gosh! It deleted everything. This is why you have to store stuff. Okay. In any case, what we had was call me equals P32 8048. I think 54AB. 5AB. Oops. Okay, E equals create our environment. Nope. Has to be SP here for I in range 10. And P equals process home Alloca, M equals E, and P dot send line -82, P dot send line. So that now that the C wasn't working, FFC 8000, let's try something like FFB 8000. Oops. So let's try that. And just to make sure that they don't steal our stuff again, we can go ahead and just copy this into a notepad. Okay. Let's try that. Hopefully this works. Okay, so still nothing. Okay, this time we didn't get an exit here. So perhaps we got a shell, and indeed we got a shell. So who am I? Allocate. So let's go home. Okay, and after counting the flags, sorry, I stand corrected. It is hard to make secure software. Okay, so I hope you enjoyed that. It was kind of long, but of course, anything which requires kind of a guessing where it's gonna hit is gonna take a while to implement. But in general, we saw how um, allocate is really nothing more than just 10 or so assembly instructions that does not care what the input is, does not check that it's positive, and if it is not positive, if it does not uh, kind of follow the rules that you'd expect it to, then the whole stack implementation is kind of messed up, and we're able to get arbitrary code execution and all that bad stuff. So again, I hope you enjoyed, and I'll see you in the next exploit.